another fire killed more than 100 people due to an illegal chemicals warehouse.
Why does this always happen? Whenever there is a chemical fire in Puran Dhaka, it does not just stay in warehouse. It tears right through the walls and spread to all the surrounding houses.
It's the concrete, Momita. At 800 degrees Celsius, the moisture builds up and turns into a high pressure steam. With nowhere to vent, the wall literally just explodes. It's called explosive spilling. Once the wall explodes, the fire breaks out.
Explode? That's insane. Didn't you say that your team was working on fix for that? Some new type of concrete that can actually breathe and handle the heat without exploding.
Yes, we just finished working on that. Do you want to see that video?
Show me.
Introducing the sacrificial containment bunker. The core of this innovation is the material itself, engineered geopolymer composite EGC. Unlike conventional concrete that shatters under pressure, EGC is a highly bendable, strain-hardening material. It possesses an extraordinary tensile strain capacity up to 18%. Instead of failing violently, it absorbs kinetic energy by distributing stress across thousands of tight microcracks. The study uses automated 3D concrete printing to extrude this advanced material into a double-layer wall stabilized by a continuous zigzag internal lattice. However, sealing a high-risk structure completely turns it into a pressure bomb during a chemical fire. To prevent this, the bunker is capped with a highly engineered lightweight steel roof.
In this study, a cement-free mix design was developed using the absolute volume method for ACI 211.1R. The binder is a precise ternary blend, 40% fly ash and 30% metacooling, meeting ASTM-C 618 plus 30% GGBS meeting ASTM-C 989. For 3D extrusion, we locked the sand to binder ratio at 1.5, a liquid to binder ratio 0.45, and a 2% fiber volume per ACI 544.1R. Using XRF, the geopolymer system uses an exact silica to aluminum ratio of 3.05, ensuring a dense cross-linked network for strength and durability. The GGBS in the precursor provides calcium oxide, enabling rapid CHS gel formation at ambient temperature. This allows ambient curing without heat, while offering early strength and control settings suitable for 3D printing. Using ML, we used a BNN model to predict tensile ductility of PBA EGC composite. Experimentally, the tensile strain capacity reached 18%, while the model predicted around 17.5%, only about 2.8% difference, showing excellent agreement. The model achieved excellent performance with R-square 0.995, MAE 0.16, and RMSE 0.196, confirming high accuracy. In the validation plot, predicted results closely follow experimental data, and the 95% reliability buffer captures uncertainty, making the model both accurate and reliable for safe structural design. EGC was chosen mainly for its sustainability benefits. It's produced around 590 kilograms of carbon dioxide compared to about 750 kilograms of ECC. This reduction comes from lowering cement use and adopting a more eco-friendly activator system. A major contributor to emissions is sodium silicate. From analysis, it accounts nearly for 45% of the total carbon dioxide, making it the largest source. Along with sodium hydroxide and PVA fiber, it forms majority of the environmental impact. In geopolymer concrete, activators typically include sodium silicate and sodium hydroxide. However, replacing sodium silicate with alternatives like rice husk can significantly reduce emissions. So, by targeting high-impact materials, EGC becomes a more sustainability and environmentally responsible solution.
To achieve this required explosive resilience, our proposed design disperses high-performance PVA fibers into the dense matrix during the final mixing stage. These specific fibers feature an elongation capacity of 6%. When a blast wave impacts the structure, extreme stress initiates tiny microcracks. Naturally, PVA fibers possess hydroxyl groups on their surface, creating an incredibly strong chemical bond with the concrete. But under explosive shock waves, this bond is actually too strong, causing the untreated fibers to instantly snap. Our solution leverages a precise 1.2% oil coating on the fibers. By engineering this treatment, We suppress the chemical adhesion, forcing a steady frictional pullout instead of a sudden rupture. This friction triggers a critical property called the strain hardening, where the material continues to carry increasing loads as it stretches. Ultimately, this micromechanical slip is projected to elevate our wall's tensile strain capacity up to 18%.
3D printing here utilizes a 20 mm circular nozzle with a precise printing speed of 25 mm per second. During this extrusion, AI computer vision cameras monitor the structure in real time. They continuously analyze the layer height and width, detecting any microscopic buckling or pore adhesion to guarantee a flawless containment shield. PVA fiber naturally melt at 230 degrees Celsius, leaving behind microscopic capillary channels. The pressurized internal steam simply vents through this path without explosive spilling. Even under normal weathering, EDC maintains itself. Environmental moisture penetrates the microcracks, triggering unreacted geopolymer particles to undergo secondary reaction. This forms aluminosilicate gel and calcium carbonate, which physically seal the fracture and restore the wall's integrity.
By combining the dynamic ductility and thermal venting of EGC with AI-driven mix optimization and automated 3D printing, we have engineered a system that absorbs kinetic blast and neutralizes thermal threats, entirely protecting the surrounding urban environment. But this is not just theoretical innovation. United States Air Force Research Laboratory has already adopted geopolymer technology for rapid runway repair, restoring damaged airfields within hours. Beyond runways, research is also advancing blast-resistant geopolymer bunkers, proving its potential for both rapid construction and military defense infrastructure.